Greetings, friends. Welcome to the post-thermodynamics world of 4C. Now that we are done talking about thermodynamics, and it's done and over with, and I hope the celebration went well for you, we are moving into optics. So this week, we have PLC 6, which is basically on the beginnings of reflection, and mirror images. And we will also talk a little bit about refraction as well this week. But I'll get homework 4. That will post probably tonight. Posts tonight. Okay. And we'll think about a due date for that one as time arrives. And usual idea of having a quiz along with the homework turn in. So we're going to start with a basically brand new phenomenon that is, well, not brand new, but new for this class. So we're going to start talking about optics, and I guess I want to begin not knowing exactly how much each of you knows about optics. So we're going to begin somewhere where hopefully it makes sense, and we're going to use terminology. And if I'm using terminology, I'll try to define all my terminology. But if I'm using terminology that you're not understanding, just please let me know. We're going to start off talking about optics, and we have 3 essential models that we're going to look at through the course of the next 5 weeks or so, and it'll be the same type of paradigm as the thermo section. So we'll do homework on optics and PLCs and labs, and then we'll have another celebration 2 will be on optics only, and then we'll move into 3, which is the last section of the class, and that'll be on modern physics, relativity and quantum mechanics, and we'll then end that with the final celebration, which will be a look back at sections 1 and 2, as well as being a celebration on section 3. So we have, as I mentioned, essentially 3 models of optics, of light. So there's a couple of things to realize. Kind of maybe as with thermodynamics, our senses are not always the best, most reliable predictors of what's happening. So when we dip a finger into hot water and go, "Oh, that's hot water," or ice water, and we say, "Oh, that's cold." Well, it's not necessarily that we are directly measuring the temperatures of things, right? We're kind of like gauges, in the same sense that a pressure gauge doesn't ever measure the absolute pressure unless you tell it to. A typical pressure gauge that you would use on a tire or something like that measures what's called the gauge pressure. And the gauge pressure is how much different from atmospheric pressure is the thing. We're kind of the same way. We measure temperature differences. In other words, we're not measuring, we're sensing heat flow, right? We put our finger into hot water and we say, "That's hot," because we experience the sensation of heat coming into our finger, and likewise heat leaving our finger if we put it in ice water. We're not actually sensing temperature directly, because at room temperature or at slightly greater than room temperature, which is your skin temperature, you feel no heat in or out. You feel no temperature sensation. So you're basically saying that that's kind of zero, just like the pressure gauge does, and that when you have a hot object or a cold object, you're measuring temperatures relative to your skin, right? Or you're measuring heat flows in and out of your skin. So the same thing is true with optics. We're not great at measuring things with our senses. In other words, the only way we sense light is by having it directly hit us in the eyeball and go into this jelly-like sac that's embedded in your skull, and having it make images on the back of a screen, which is then transferred via your optic nerve into your brain, and your brain somehow makes something of this. All right? So when we look at what light is doing, you might find it easy to say, well, we can get fooled, right, fairly easily. We could say, oh, I see this is over here, but it's not over there, it's somewhere else, and that's because of how the light is entering our eye. So based on that, we have a couple of different ways of looking at light. We have three models of light. I want to just kind of put forth here that the word light, as I use it in this class, is indicative not just of the visible spectrum. Usually it means all electromagnetic radiation. Certainly the visible spectrum is useful for us, but holds no significant place above any other radiation. So visible light, I'll usually try to say visible if I'm talking about light that we're seeing. But light in general will mean any electromagnetic radiation. And we characterize electromagnetic radiation by, well, essentially a single number. The wavelength is typically the easiest way to do it. So we characterize that single number is known as the wavelength. And we try to divide up our electromagnetic radiations into different bins because we're humans and we really love to categorize things. What we do is we try to say, oh, if you have a wavelength between the X and Y, we're going to call you this type of wave, electromagnetic radiation, whatever. If you have one between here and here, we're going to call you this. If we have one between here and here, we call it this. Of course, these boundaries are not sharp, and they are imposed by people. Nonetheless, it's useful to kind of have an idea of approximately what wavelength is representative of each kind of type of electromagnetic radiation. Let's see here. With that, I would like to show you a picture of the electromagnetic spectrum. Whoops. Sorry, here we are. And I'm just going to share my screen here so that you can take a look at this. All right. And we're going to go here, and we're going to go here. Alrighty, so we've got this. This is the electromagnetic spectrum. We're good? Can you see that? Hopefully the answer is yes. What we have is, like I said, these boundaries are not supposed to be quite so sharp. Nonetheless, what we have is basically bins, categories into which we divide the different type of radiations. Radio waves, microwaves, right? You can kind of see these are all in a general category here, AM, FM, and microwaves. And I've got the frequency up top. Mostly, we're going to talk about the wavelength. The frequency is useful when you're tuning a radio, for example, right? So if you think about the frequency on the dial, you're going to want to know what AM or FM station you're tuning into, and that's all well and good. Typically, if it's physics and science, we're going to talk the wavelength because the frequency just gets to be too big of a number. Huh?
I don't think we can see anything. Sorry about that.
Well, all right. So this is not coming through?
No.
Okay, well then you don't get to see it. So we've got radio waves over here. And we've talked about wavelengths. So the wavelength of these things is going to be probably somewhere in, oops, I'm going to say wavelength. Talk about wavelength here. So the wavelength range of radio waves, typically between about, say, a meter or maybe a little bit less. If you're thinking microwaves, if you're putting a lump microwaves into this, you're going to talk about something that's in the centimeter range. Radar is a microwave, and so that's going to be probably between 1 and 3 centimeters. If you're going to lump in all of the AM, FM, and all of the other stuff, you're going to look at having a range which is probably somewhere near 1 centimeter to about, say, 10 to the 4th meters. They can get really large. And it's not uncommon to have wavelengths in the kilometer range for signals that are transcontinental, right? So you'll be able to listen to, for example, BBC radio, and that's not direct line of sight because Earth is curved. If you're not, just in case you didn't know, so they're actually kind of below the horizon to us, which means that it has to bounce off the atmosphere in order to get to us. And in order to do that, you have to have a reasonably large wavelength. So you're going to look at radio waves and microwaves, if you put those in here. Infrared would be your next category. This is typically in the micron stage, which means it's millimeter and lower. So you for infrared, you'd be looking, somewhere typical is probably 10 to the minus 4th of a meter or so. This is I'll put it in 10 to the minus 2 for meters here. So I'm going to do meters. So this is around 10 to the minus 4 meters. Are visible here is actually a really small fraction of the entire spectrum. So we're looking here at visible, and it's typically somewhere in the it's usual to know it in the hundreds of nanometers, which means it's around 10 to the minus 7 or so of a meter. And our color spectrum would start with red out on the infrared side and go up by Roy G. Biv to the violets on the right-hand side over there, and you're going to get to the shorter wavelengths up here. This just for kind of having numbers off the top of your head. You're going to look at something around 700-ish nanometers for red. You're going to look around 400 for blue, right? Nano being 10 to the minus 9. It's a nice, easy set of numbers to keep. That your visible spectrum is about between 400 and 700 nanometers. Of course, after the violet, we're going to go to the ultraviolet. And wavelengths of that, you're going to be looking probably somewhere in the 10 to the minus like 8-ish is right, one less, 10 to the minus 8 or so. And you have UVA, UVB, and UVC, and these are all categorized, and I don't quite remember which goes where. After that, X-rays, and after that, gamma rays. And these are getting to be extremely small wavelengths. So X-rays, you're looking 10 to the minus 10 perhaps, 10 to the minus 11, which is, this is a tenth of a nanometer, and is really useful for probing atomic structure because atoms are about that size. And then gamma rays are coming out of nuclear reactions. They're quite tiny. They're 10 to the minus 16 is the upper limit of these. Really good for probing nuclei. Nuclei are about that size, as it turns out. So though it's just telling you how light is useful as a probe to look into microscopic matter. All right, so we characterize by one number basically all of this radiation, okay? Now, the wavelength we're going to call the Greek letter lambda. That's fairly universal. And we're going to look at the three different models of light. The three different models of light are essentially chronological. And now we can give good reasons as to why we have these models of light. So our first one incorporates the idea that whatever equipment you have, if you're going to look and try and sense light with a detector, if it's your eye as the detector, fine. If you have a light meter or a light detector or something like that, fine. This first one is going to be situations in which the object that the light is interacting with is much larger than the wavelength of the light. The wavelength of light is small compared to the size of your object. All right, so we'll just say lambda is small in comparison to the size of the object that, I mean, it could be even like a hole in a wall, right? Something like that. How big is the hole compared to the size of the light's wavelength? Well, it depends on the wavelength. But if it's visible light, and you're looking at a doorway, well, that's really big compared to the size of the wavelength of visible light. It's not that big. The doorway is much smaller than, for example, a radio wave. So its comparison is small compared to the object, or whatever it is that's doing the sensing, okay? So here, we also are going to talk a little bit about, I'm going to dip in a little bit to photons. Photons kind of comprises the quantum mechanical view of things, and perhaps you've heard of these, perhaps not. But the energies, the photon energies are small, okay? Photon energies are small. That is to say that the light doesn't carry very much energy compared to the sensitivities of the things, right? So we're going to be able to sense only very large amounts, but the individual photons are smaller than that. Photon energies are small. when you're comparing it to the sensitivity of the equipment. Okay. Therefore, what we find from this model of light is that light essentially travels in straight lines. And just a sec, am I plugged? Let's make sure I'm plugged in here. Yeah, okay. And so light travels in essentially straight lines, and we call them rays. Essentially, they're beams of light. And therefore, this could be known as the ray model. This is known as the ray model of light. And you'll come to find out that essentially when we work with the ray model of light, we're thinking about the geometry of what the light's doing. How are the light rays moving, and where are they propagating? So this is known as geometric optics. Number 2 here is the idea that the wavelength is no longer small compared to the size of the object. Okay, I can give you an idea. If you think of, for example, this is a one of those pen lasers, laser pointers. So what happens, right? You can kind of get an idea that the ray model is very straightforward and useful because it says that light travels in straight lines, which if you look at this, which I don't think this is quite going to come through very well, but if I shine this laser here, so you can see the dot on the whiteboard, and if I hold it so it's almost parallel with the whiteboard here, then put something in its way so that it can direct some light towards the camera. Not sure if you're going to be able to see this, but no, I don't see it too well here. I see it pretty well over there, though. I don't think you can see that too well. Oh well. Just another thing for you. Another thing you can't see. If I take a laser pointer, right? It's the model of rays is essentially what's emitted from a laser beam. Now, make no mistake, we can never isolate one single ray of light. So even though a laser is fairly small collimated beam, it doesn't comprise a single ray of light. This is still a bundle. All right. So what you think about when you think of rays is like light traveling in straight lines as if emitted by a laser pointer or something like that, but knowing that it's not just a single thing by itself. So the wavelength is small compared to the objects, and so things that are large, let's see here, things that are large, well, so I've got a prism of acrylic here, and if I kind of hold it there, and I'm going to have my light interact with this thing, well, okay, fine, it's going to do stuff, right? It's going to, if I try to show you what path this is taking by just moving the dot back and forth, right? I can come up here. Let's go here. Right? You can see that the light is coming out up there on a very different path than where I'm shining it in, and I'm shining it in on this path here, but it's going in and coming out like that. You can see that it's going through the block between there and there. But nonetheless, it seems to be traveling in straight lines, right? It's traveling, that's a straight line path from here, as it leaves the block and goes off that way, okay? So in the ray model, we're talking about independent rays of light, and we're talking about straight line motion, and we're looking at the geometry of the situation. And that's going to be the model we're going to start with. The next one is one in which the wavelength is larger and approximately the same size as some of the objects. But the energies are still small. Just as in the ray model, it's still small compared to the sensitivity of equipment. Okay, so that's the situation in which when the wavelength becomes approximately near the size of an object, then you start getting different results. So to give you an example of that, I have this laser, which is green, and I have a bunch of small apertures. Okay, I have a bunch of small apertures here. Let's see, we're going to go and take a look at this one. Now, again, this is probably not something you're going to be able to see, but if I go and shine that thing here so it's going like that, there it is. Let's see here if I can get that to just be down a little ways, and that's right about there, like so. All right, so not sure if you can see this. This is a small beam of light that is coming through a slit. So what I've done is the laser is shined, and what I've put in its way is basically a narrow cut, as if I've taken a piece of paper or something and a razor blade and just made a small cut. The light's going through that, so the slit size, while not exactly equal to the wavelength, it's not tenths of a micron, right? It's maybe 4 or 5 times, but it's in that range, right? It's near to it. What I'm going to do is I'm going to actually switch this to a much narrower slit, and then I'll move the camera so that you can maybe see, and go to this one, so that you can maybe see the difference. Let's see, that one's not coming out quite as well. Yeah, maybe I do like the first one. That. Yeah, the first one's nicer because it's letting a little bit of light through, so let's have that. All right, okay, so I'm going to show you this pattern of light. So this is what happens when a beam of light from a laser tries to go through a narrow slit. And just for a frame of reference here, the slit is about, it's looking like it's about 2/100ths of a millimeter. All right, well, that puts it at 20 microns, which is not near 0.1, but it's closer to that than others. And we'll see if you can see this. I'll just move you up in here. But if I do that, I'm going to need to unplug this. So we'll take that off now and do that. All right, so let's see if I can show you this. For your first demonstration of the day, I can going to show you that right there. If you can see that the light kind of has, I have to tip it so you're not blocking the actual light, but if you look at it, there's a large kind of central maximum right in here, and if you can kind of see, there's little itty bits of there's little itty bits of light kind of coming off to the side out here in kind of like fringe patterns. So if you can see that, then what's happening is the light's going through a slit. That's all it's doing. And from a ray model point of view, there's no reason for light to not just go in a straight line, go through the slit, and keep going. So this is indicating that we've got new things to think about, things that aren't covered by the ray model. All right. The idea that light can go through a small slit and then change direction. There's no reason for that here in the ray model. Okay. So this is the situation in which the wavelength is about the size of the object, and we therefore call this the wave model. Because that behavior that I just showed you is definitely seen if you go and look at any. I mean, the easiest example for me would be if you go to natural bridges and you look at the big rock in the middle of that's off to the side of the beach there, that's in the water. You can see the pattern that the incoming water waves make with the pattern that they make with the rock in the ocean, and you'll see that they change direction. And you'll see that they kind of move around, and they do this, and they do that, and when they go into if you've ever seen water waves going into a small opening, through a small opening, they spread out. So this is essentially light mimicking that type of behavior. When we talk about what kind of model we're going to give this, we call this the geometric model. This is called the physical model. Oops, physical optics. It's called physical optics. And let's see, I gotta plug this back in. All right, is that all right? Let's see here. All right, lastly, we're gonna go to the, so things are fairly simple and straightforward for the ray model. They get more complicated because this is essentially an extension of classical electromagnetism, and that gets to be more interesting, a little bit more complex. We're going to move back to number 3 here, which is a slightly simpler picture, which is known as the photon model, and it's the one in which the wavelength is large compared to the things that it's interacting with. And that the energies are also comparatively similar sized or large. Or I should say, yeah, the energies are comparatively sized to the interactions that it could have, right? Like on an atomic level. Wavelength is large, energies are large. And this is the quantum mechanical viewpoint of light, and it's known as the photon model. This is a situation in which we now consider the light to be made up of a stream of particles. Right, so this is essentially the particle picture. And it's known as the photon model. So, those are the 3 things we're going to be looking at, and we're going to take them in that order. So, what we'll do is we're going to start with ray optics and look at what is going on when light, in which we can ignore the wavelength because it's so tiny, and we can ignore any energetic features of the light because the energy is small enough that we don't really care about it doing lots of things. We're going to take a look at the start of geometric optics. let's start by taking a look at reflection. And so, reflection off a mirror, you probably are all quite aware of reflection, and no big deal, but let's put it on a bit more of a scientific grounding here. And let's talk about the law of reflection. So the idea here is that you can make an observation, kind of the way science proceeds. You make an observation, and you then measure things. You get numbers that reflect the measurements, and you come up with a law that then summarizes all of the numbers and the measurements. Okay, so for example, Newton's second law, comes into play when you have to calculate the acceleration of something, and there are forces acting, and you sum them all up and figure out what the acceleration is, right? And this comes about because of years and years and years of people pushing on things and watching them move in different ways. Okay, so the laws are there to summarize the measurements and the numbers to make predictions. Okay? But the real glory and the grandness of science is when you can come up with a way of thinking such that the laws become evident. Okay, so the idea that you walk around and you think in a way such that you go, oh, I know what's going to happen here because I'm thinking of light as moving this way, or I'm thinking of forces as being doing such and such, right? And this has been the goal of physics for more than 150 years, is to try and synthesize a way of thinking such that all of the laws that have been discovered along the way by humanity are evident. And it's in doing this that we lose most people, because the way of thinking is just so wildly crazy and outside of our norms that it's hard to stomach. Okay, it's hard to say, well, wait a minute, how can thinking about it this way be right? Well, because it's backed up by trying to think of laws and numbers and measurements and observations of hundreds of years of these things. So let's take a look at reflection. I'm gonna have a point A here, and I'm gonna have a point B, and we're gonna put a mirror here. Like this, I'll just call this mirror M. And oh shoot, I didn't bring in my straight edge. Let's see if we have one in here. No, doesn't look like it. Okay, we're gonna be freehanding. So, okay, question here is, if I put a light source at point A, how is it going to arrive at point B? What would be its way of arriving at point B? And the answer is, it would just go straight to point B. Because in the ray model, light travels in straight lines. Seems simple enough. I want to get light from point A to B, it goes straight from A to B. Now let's put in the requirement that it actually strike the mirror. Okay, I'm just going to put it in so that light strikes the mirror. I'm going to say, okay, well, how is light going to reach point A to point B? And the law of reflection is that it's going to do so in a way that the reflected angle is equal to the incident angle. All right, so that means what I have to do here is think about Light's going to take a path. Light's going to take a path from here to here, and then it's going to go from here to there. Whoops. There we go, like that, such that these two angles are equal. Now, we're going to start off with this, but we never measure those two angles. But the law of reflection is that these two angles are equal, which means also that if I drop a normal to this mirror, and I say, okay, I'm going to have a normal to the mirror, right there. If those two angles are equal, then certainly these two angles are also equal. And because of how we need to proceed, we're going to always be measuring angles with respect to the normal. All right? If you do these, it tends to louse things up. So I'm just going to move these out of here. And we're going to look at these two as being the angles that we're going to be interested in. Here is the reflected angle, it's called theta r. Here's the incident angle, it's theta I. And the angle of reflection is equal to the angle of incidence. And that's the law of reflection. Notice once again, these are straight lines, paths, as dictated by the ray model. There's no reason for it to be anything other than straight line paths. And they proceed directly from here to there and then from there to there. So they do change direction, right? In the ray model, you have to have a reason to change direction, and the reason is it reflected off a mirror. Okay, so now let's take a look at another situation in which light rays change direction, and it's called refraction. And I'm going to do the same type of thing where I'm going to take a point A and a point B. I'm going to try to get light from point A to point B. How is it going to do that? Well, now I'm going to throw in an additional requirement that point B is actually in a material that is different than the material that point A is in. So let's make a boundary between these two materials, which is, say, here. And let's suppose, for example, that this is air and water or something like that, right? I'm looking at something that's underwater. Okay, and now my question is, what path does light take such that it goes from A to B? And it still travels in straight lines. Well, once again, it turns out that if I connect these two with a dashed line here, light does not take that path. Okay. What light actually does is it tries to get from here to there, and from here, too late, I already did it this way, so I'm from here to there. So there's a bending at the interface, okay? There's a bending at the interface, and if I draw the normal to the surface once again, I'm going to talk about these angles. Again, theta I for theta incident, and theta R here for theta refracted. Okay, yes, this is theta R, and yes, this is theta R, and yes, they are different angles because they are different physical phenomena. So you'll have to understand from context which theta R we're talking about. This is a description of the exact thing you were just looking at when I held the block up here with the laser pointer, and you noted that when I shined it in here, I'm going almost vertically here, and it hits this boundary right there, okay? Hits the boundary, and it would be going, I don't know, let's see here, if I take this away, right? It is going to go in a straight line, but if I put this block in the way, now it hits the block, and it kind of, right? You can see that it's changing its path of travel when it's in the block, okay?
So what's happening is it's going up and down here, it's going into the block, and now it's at an angle right in there. This is the vertical path, or the near vertical path, I'm sorry, it's not vertical anymore. Here's the near vertical path. And it's going from here to there, and then you can see it's coming out up here at definitely a different angle. If you can just see that thing moving around on the board right there. Okay? I could try to do it in a slightly darker area over here, if that helps. Right, we're going like that, changing direction inside here, and then going out at an even different angle there. Okay? Every time there's a difference in the media in which it's traveling, it's going from one medium to another medium. That's what these things are called. It experiences a change in direction, and this was noted by Ptolemy. And if you're aware of the name Ptolemy, he was the one who kind of tried to put together a catalog of planetary motions and come up with how the planets are arranged, or really how the sun and solar system is arranged around Earth. And it was pretty complicated because it's not arranged that way. But he came in and said, I'm going to measure these angles in which light refracts in water. And he measured these in like 100, in about year 100 or so. And it took until 1620 before someone came up with a mathematical description for this. And the person was named Snell, Willibord Snell, and he was Dutch, and this was, like I said, 1500 years later. So Snell came along with the description of what's going on here, and Snell says, well, if you take the sine of angle theta I, and you equate it to the sine of the angle theta r, these two sines are going to be equivalent as long as you multiply the sine of theta r by some number, right? So he was working off air to water, okay? So this number n, just some number, and the number characterized air to water. And if it was a different material, like going air to glass, well, then the number n was different. So it kind of somehow characterized the material. Okay? This is a number that's related to the materials involved. Now, I'll cut to the chase a little bit here and say that that number n is now known, due to what I'm about to explain to you, it's now known as the index of refraction. And it characterizes, in fact, the speed of the light within the material. Okay, so according to Snell, we don't know anything about the physics of this number. Snell was a mathematician, so he didn't know anything about physics. Well, it was the 1600s, so mathematicians actually knew a little bit about physics back then. He didn't know what this number was kind of going on about, and it was a while before people realized, actually, this is the index. And when that happened, that was because Maxwell had come along and described classical electrodynamics. So that happened in about 1860. So it was another couple hundred years after that. And this is a pretty long process. I'm trying to summarize essentially almost 2,000 years of discovery in about an hour and a half. So there you go. This is known as the index of refraction. And we'll talk more about that later, but like I said, it essentially, as we know now, it characterizes the speed of light relatively in the two media. Okay, so now that we know, I should have done this. Law of reflection, I did that. So this is kind of Snell's law. I should have put that up here. Snell's law. Because I started this whole thing talking about observations. We observe
the light bounces off things, and we observe that light changes path when it goes from one to another, like in a transparent medium. So we come up with measurements, and we come up with laws that describe those measurements. Now let's come up with a way of thinking such that these two laws are evident. And that's what I've been working towards right here. Now, this, I'm going to draw these same two pictures again. I'm just going to erase all of it. I'm going to draw them again. And I want to come up with a way to think such that I can kind of go around with this way of thinking such that I already know that these two laws are going to happen. This was first proposed, it was a long time ago. Hero of Alexandria kind of thought about this first initially, but it wasn't quite right. And it wasn't until the middle 1600s, about 1650, that Fermat came along and said, well, let's think about it slightly differently. So this is known as Fermat's principle. And it's a way of thinking such that the law of reflections and Snell's law of refraction, are more evident, right? Like they just happen because you're thinking of things this way. Now, you may also see this as referred to by the name principle of least time, or the Fermat's principle of minimum time, or something like that. That's not quite true, even though when he came up with it, that's what he was thinking. Because Hero of Alexandria actually thought about it being the principle of shortest distance. And let's see why first. And we'll talk more about this. So let's go through and look at the reflection again, where I've got my point A here, and I've got point B here. And we're going to put a mirror here. Okay, my mirror here is called M. And we're going to do the same thing. How does light at source A here? I'm going to put a light source at A, and I'm going to ask, how does light travel to B? And you're going to say, well, it goes in a straight line, because the shortest time would be the shortest distance, right? So if it wanted to get light from A to B, then it would just go straight from A to B. That would be the shortest distance, and therefore that would be the shortest time. And this is why Hero thought light travels in the path of shortest distance. Fermat came along and said, well, when we look at refraction, you'll see why. But Fermat said, let's think about least time. Okay. So the idea is, if we now reintroduce the idea of light going from A, hitting the mirror, and then going to B, what path will light take? And according to Fermat, he says, well, it's going to be the one of the shortest time, which again is not, in this case it'll work out fine. How are the rays of light going from A to B via the mirror? So how do we know, for example, that light doesn't just go straight down here, like that, and then go that way, reflect up this way? How do we know this is not the path? Well, and here's where Fermat's principle really starts to show how beautiful it is. If I take a slightly different path, a neighboring path, and I say, okay, let's call this, I don't know, point D or something, because I'm going to use point C for later, so let's call that point D. So what if I take a neighboring path? I'm going to take the path right here. I'm going to do this in pink. I'm going to take a path right next door, where I'm going to say the light's going to go from here to here, like that, to here at point E, and then it's going to go up to point B. Okay, so now it's going, whoops, like that. Like so. Okay, what have we learned here? If we want light to take the shortest timed path, then in this case, it will have to be the shortest distance path, because light's traveling at the same speed in all these paths. Therefore, if I can show you that path AEB is shorter in distance than path ADB, then we know it's more likely to take the AEB path because that's the shorter time path. Because it's the shorter distance path and light has the same speed in all these paths. So take a quick look here. If I take a look and see how much longer is path AE than path AD, I'm going to say, well, it's basically what you would have to do is take a compass and kind of, and go like this. What we're going to do is just trap a normal here. So I'm going to drop a normal from AE down into D. And I'm going to say, how much different is this path? About there. That's my normal. So this distance here, that distance right there, is how much extra I have to travel on path AE than path AD. This is how much greater of a distance I have to travel just on the first leg here. Okay, so I'm losing if I'm going on path AE right now. But now let's take a look at these other paths. How much different are these two paths from one another? And I think I think even on Zoom maybe you'd be able to see this, but I'm not sure. This distance right here, I'm going to make it slightly bigger. This distance right here is how much I am shorter on path EB than path DB. And my hope is that you can see that distance, and I'm going to extend these lines so you can see them. This distance, if you can see my two marks here, can you see this distance here is shorter than this distance here? Right? So what that means is I had to travel this much extra in the first part, going from A to E, but I saved this much going E to B. So path AEB is definitely shorter because I had to add this, but then I subtracted this, and this is larger. All right, so therefore my path AEB is lower distance. It's a shorter distance, and therefore will take light, which travels at constant speed all throughout this, a shorter time. All right? Where's Fermat's principle coming in here? Well, the question is, what does light do? Well, light's going to try and find the shortest possible path. Where is that? We use, of course, geometry to find the answer. How do we find this answer? Well, I would show you this picture, but I guess the Zoom isn't working on showing screen shares. So, sorry. But what you do is you think about the distance it takes from the mirror to B. What's that distance? I'm going to take another point that's exactly this distance underneath the mirror to there. I'm going to call this B prime, such that these two distances are the same. Okay? And now, I'm going to remove the mirror and ask, how do I get light from A to B prime? And I say, well, it travels on a straight line, so I'm just going to draw that straight line. The straight line goes from A to B prime, like so. That would be the shortest path between A and B prime. Got a little curve in it there, sorry, but too bad. Close enough for government work. That would be the shortest path, and therefore the shortest distance, and therefore the shortest time for light to get from A to B prime. Well, I'm going to now put the mirror back in. I'm going to say, imagine that light comes to that point right there on the mirror. I'm going to call that point C, and then reflects up to point B. So, if I take this path, and I know that's the shortest path, then what I'm going to know is, since I've constructed this side to equal this side, you see how geometry is coming into this now? Suppose I've constructed this path to be the same as that path. In other words, since FB distance is the same as FB prime, then the angle right here and right here, those two angles must be equal, right? Because FC is also equal, and these are two similar triangles. Therefore, angle BCF is equal to angle B prime CF. Okay? And if I need a little bit of room here, if I just take these two out, and I drop in my normal to the mirror, right, then the angle here, which is called the reflected angle, theta r, is the complement to BCF. But maybe you can notice by parallel angles, right, this angle here is the same as this angle here, which is to say ACE. So BCF and BCF, and that's equal to ACE, that angle there, which means that this is the complement to that angle, and that's theta I. Okay? Therefore, theta I equals theta R, or really it's the other way around by causality. Theta R is equal to theta I, right? And that we've shown is the law of reflection. So just by a quick proof of light travels in straight lines, and light takes the shortest path, we can show you that the law of reflection works. Okay, now, Hiro said shortest distance, Fermat said shortest time. Right now it has made no difference. Let's now look at a situation in which it makes a difference. And that would be the refraction situation. Incidentally, if you ever play billiards, this is how you win. Now, assuming that you're getting pretty reasonably elastic perfect collisions with the ball off a bumper, what you do if you want to make a shot where you have to go off a bumper and go around something and go into like a corner pocket or the middle pocket, what you do, right, is you're going to think about the ball that's going to have to hit the bumper and go off to the pocket. And what you do in your mind is create that pocket down here, and you shoot the ball at that pocket there, and it goes that way instead. And you have made a lot of money because now you're really good at playing pool. But I guess if that was true, then we wouldn't be here doing this. I'm going to redraw that picture that I drew of refraction down there last time. So I'm going to draw this again, my points A and B. I have a medium. Where's my medium? Medium changes here. Wow. That's interesting. I'll be right back. Good. I guess I haven't been moving around enough to keep the lights on. All right, so here's my medium. This is once again, for example, air, water. And I'm going to go over here to point B. And I'm going to ask, how do we get from point A to point B in the shortest time? Why Fermat thought of this. Okay, because the shortest distance, right, we already know that. But now we have the caveat that light travels slightly slower. It's at a different speed here in the water. Okay, this is a lower speed. This has a lower light speed than in air. So now we're asking, how do we get A to B with the caveat that I'm going to be slower here. The idea being that you're a lifeguard here at point A and someone is shouting for help. I'm on a surfboard and there's a shark and it thinks I'm an appetizer or whatever. Somebody's shouting for help at point B, right? The surfboard otter is coming towards me. Oh, it got eaten by a shark. Never mind. Well, anyway, point being here that I want to get from A to B in the shortest time because this is a life-threatening emergency. So naturally, being people, you'd say,
go right at it. But this is where we don't make good lifeguards, because we have to stop and we have to think and compute what the actual path should be. So what you want to say is, okay, should I just go straight there? That would be the shortest distance. Well, what if I imagined doing that, okay? And I'm going to trace out a quick dashed line here, from here to here. What if I imagined doing that? But now I'm going to think, wait a minute, I can run on the beach a lot quicker than I can swim in the water. So if I get a little closer to point B before going into swim, I will have saved myself some time, certainly not distance. I'm going to run a greater distance, which feels wrong, but I'm going to have saved time getting from here, from point A to the shoreline. And then I jump in and go in the water, but I'm going to take a path here. So then you say, well, why don't you just go all the way out to here like that and then come straight down, because that minimizes the amount of time that you're in the water. Well, yeah, but it also really adds a lot because I'm running at this crazy path here. So what we know by experiment is that the correct path is one in which the light goes something like this, like so, because that is the shortest time distance. Now, here is the point where the light crosses the boundary, and we can do the same type of thing as we did before. But what I'm going to do is I'm going to think of this as the correct path, and I'm going to think of adjusting this path slightly. Why are we doing that? Well, I'm going to go back to what Fermat's principle was initially introduced as and what we've kind of come to see it as. Fermat's principle was the principle of least time. But that's not quite true. It's really the principle of paths in which there are no first order changes in the amount of time taken, although there are possibly second order changes principle. But that's a lot to say, and I don't really want to give a class on the principle of light taking the path of nearby other paths having zero first order differences but a second order difference principle, because nobody would be interested in that. So let's assume that we take this path here at point C and there's a neighboring path here at, say, point X, in which it's so close to point C that it's essentially almost the same path, right? So you'd say, well, if I thought of the time that the path took, right, then I might find there's something like this, and at the very bottom here, that's point C. Point C would be there. And I'm talking about point X. Point X is right here. And point X is really close, but has no first order change. So the principle isn't shortest, it's the one in which there's no first order change. However, that doesn't always mean minimum, that just means extremum, right? So it could be minimum or it could be maximum, but it's one in which there's no first order change in the path time that the light takes. Now, once again, using geometry, I can show you, I can construct a nifty little way of thinking such that Snell's law becomes evident. I will not spend too much time doing this, but it all hinges on this path difference right here around point X and C. So let me draw that slightly larger so you can see it. Here's point C and here's point X, and light's coming in like this and leaving like that, and here light's coming in like this. It's gonna come in, how's it gonna come in? It's gonna come in slightly more, not quite parallel, so it's gonna come in like that, and then, ooh, that's not good. I want to go like this. And it's gonna leave kind of like that, that's terrible. Like that.
I'm trying to make some slight differences in these so that my reasoning will work out. Point being here that if I take a look in the same way as I did with the reflection at how much extra distance, oops, wrong one, how much extra distance does C travel? Right, that's a right angle right there. How much extra distance is involved here in this one, and it's going to be from here to there, where this is the right angle. Okay? And my goal then would be to show you that in first order, this distance right here and this distance right here are equal. Right? If this is truly a first order change, then those would be equal and this would be essentially the same path. So what you end up doing is looking at the sides of the triangle. You can say this leg of this triangle is equal to that leg of that triangle. And in order to do that, I know this hypotenuse right here is common to both of them. And therefore, if I'm looking at a common hypotenuse, I've got xc times the sine of an angle here. Call that, let's not call it theta, let's call it phi 1. I'm going to take the sine of phi 1 and I'm going to say that's going to be equal to, now in here, I'm at a lower speed, so I've got to multiply by that n factor, which compensates for the speed, and I'm going to have the sine of, this angle here, which is phi 2. Alright, so by saying that these two legs are equal, I can come up with an expression with a common hypotenuse such that the sines of these angles are equal, and all I would have to do is go back geometrically and show you that this angle is the same as if I pulled a normal at point C. All I would have to do is show you that this angle is the same as that one. This is phi 1, and this is phi 2. And I've got Snell's law here. Okay? So I'll just kind of cut that out, but let you go and explore that if you are interested. Now, interesting things that happen due to Snell's law. Things that we have applied, I'm sorry, not Snell's law, Fermat's principle. Things that we have applied Fermat's principle to are things like the most interesting one that comes to mind right away is the light collecting mirror. Right? I want to design a telescope that has a mirror to which all the light goes. Mirror that focuses light. Right? What shape does this mirror have to take in order that the light comes to a focus at one point? Okay, so you're going to think of a mirror which is getting hit by starlight. Starlight is incoming parallel. And so what's going to happen is you want to ask the question, I want to bounce this thing off here and have it go that way, such that if I bounced one off here, it would go to, say, there, right? And if I bounced one off here, it would go through there. And if I bounced one off here, it would go through there, right? That shape is because when the light rays come in and bounce and make this distance, if you compare how much extra distance this one traveled to get to the mirror than this one did, then you look at how much extra distance this one had to travel to get to here than this one did, those two distances are equal. And the reason, or the description, the way of thinking about this is such that it's equal timed because those two paths are different by the exact same amount, no matter which path you take here. And that's why the path is a parabola, right? It's a parabola which focuses the light. Anytime you have light which is getting focused to a point, it's because all of the light goes what's the path I should take? The shortest time path is therefore this, and they all do the same thing. For example, think about a lens, right? A focusing lens, which we will also examine in detail. If I want to get light from here, and I want to focus it here, how do I do that? Well, light from the source here is going to be spreading out, right? It's going to be going in all directions. Okay? I want to get as much of the light that's kind of going that way to focus at that point. Well, this is not a problem right here, right? That's easy. No problem. But that's a pretty short path. If I think about this path, the one that goes this way, I'm going to have to somehow turn that light to go this way, which means it's a longer path. That means I need to put something in the way of this path in order to extend the time. And therefore, if I put a piece of glass in here, in order to make the time of this path equal to the other paths, I need to extend the time here to make it equal to the other paths. So I'm going to put a piece of glass here. I'm going to put a piece of glass that's like that thick. And in that time, light only goes this distance because it travels slower in glass than it does in air. But if I look at this path up here, or likewise the one going down this way, I don't want the light to be hindered so much, so I'm going to have to thin the lens out a little bit. I'm going to only maybe have it go through this much, right? So by the time it gets up here, like that, now it hits this thing and turns and comes back that way. But that has the exact same amount of time as this path, and the exact same amount of time as this path. But I'm going to have to make a slightly bigger one here, so it does that. I'm just bend this a little bit later on that one, like that. So you can see I'm mapping out a lens here, which has the shape of that, because all of the paths of the light, which are going this way, are equal timed, such that they all arrive here. This is true of any focusing system. Any focusing optic system means that the paths the light are taking all have approximately equal to the first order
Time from A to B.
Okay.
So there's a little bit on the Fermat's principle. Remember, it's a path of
no first order change. It's not technically least time anymore. Anyways, that seems to be what we have come for today, so that will be the end of our class today. I'll post up some homework to get started on for you on, I'll post that up on tonight at some point, and I will say good day to you. Go enjoy looking at things that make you go, I wonder where that light came from. Alrighty? Until next time, folks, we'll see you then.